Okay, so the first problem was pretty straightforward. It was a circuit with a bunch of flip-flops and an XOR gate. Have you guys seen that circuit before? You have or you have not? You have. What is it? Huh? Yeah. What is it called? Huh? Pseudo-random. But pseudo-random is a very generic term. If you have done courses on digital communications, you would know something that's called as a maximal length sequence generator. Okay? That's what that is. So the circuit that I gave had, had 7 flip-flops, basically like a shift register, and the data from one is passed to the next, and the last two are XORed and fed back to the input. Okay, and it's running off a clock. So every clock cycle, the input to the shift register is some function of some bits in the shift register. Okay, in this particular case, it's the XOR of the last 2 bits. So all are D flip-flops. Okay. Now clearly, if all the flip-flops were initialized to 0, 0 XOR 0 is 0, and it will stay as an all 0 sequence. Okay. But if you initialize it to any other state, it turns out that how many states are there in this circuit? How many states can it have? 2 to the 7. It has 2 to the 7 states. So 7 flip-flops, 2 to the 7 states. Out of these, one of the states, that is all 0 state, is what is it? Self-sustaining. It will always stay 0. But if you initialize it to any other state, it turns out that it goes through all of the remaining 2 to the 7 states in some order and then repeats itself. Okay? Huh? No, you can have any number. So I'll just come to that. So if 0 state is self-sustaining, and if you initialize it to any other state, and it goes through all the 2 to the 7 minus 1, that is non-zero states, and repeats. So it has a periodicity of 2 to the 7 minus 1. Okay. So if you look at the single output bit, you can take any of them, any shift register output. It's just shifted version of each other, right? So let's say you take this as the output. The output has a period of 127. Okay. And this is known as a maximal length sequence generator, because that is the maximal length of the sequence that you can generate with 7 bits. Meaning 128 is the maximum, but this is called the maximal length sequence. Okay. All states of a 7 flip-flop state machine except all zeros. Okay. So it's also usually called pseudo-random. Pseudo-random, it can be anything. It doesn't have to be this maximal length sequence generator. You can generate it in other ways also. But this is also frequently called PRBS or pseudo-random bit sequence generator. And as I asked, the number doesn't have to be 7. You can have any number of flip-flops. What changes is, always you will have a certain number of flip-flops, basically arranged as a shift register, and it is clocked. And you take a certain number of them, not necessarily 2. Okay. Obviously, you will always take the last one. If you don't take the last one, then you can always omit it. Okay. It becomes an n-1 length stuff. So you can have n flip-flops. You will always take the last one, and you can take one or more of this. That particular, which ones you have to take depends on the number of flip-flops n. And for particular values of n, there are some other combinations. So you can take like maybe it's these 2, you XOR it, and in some cases you may have to take 3 of them and XOR them and feed it back, and this will give you a sequence which will have a period of 2 to the n minus 1, and this is usually referred to as a PRBS n sequence. This is a very useful block in communications, mainly because, so what is random about it? Yeah, let's talk about that first. So with 7 flip-flops, you get a sequence of period 127. Okay. So let's say this is x of n. Now you calculate the autocorrelation of this sequence, which is the summation of x of n and which is summation of x of n multiplied by x of n shifted by a certain number. Okay. And also let's say that let's define the levels to be minus 1, 1 and 1 for the two logic levels. Okay. So what is Rxx of 0? So let's say we take two periodic sequences and we shift it and sum it and we run the summation from over a 127 bit interval. So what is Rxx 0? 127, right? You multiply the sequence by itself, you get plus 1 and you are summing over 127 bits, so you get 127. What is Rxx of 1? Yeah, it turns out to be minus 1. Is it very obvious or? Yeah, but I mean it could be minus 3, right? Why is it minus 1? No, anyway, I don't think it's that obvious that it is. Because then that way, I mean, we are not even looking at the nature of the sequence. It could be any sequence and it will turn out to be minus 1. No, that's not the case. So in this case, it is minus 1 and not just Rxx of n. For any m, it is minus 1 when m is not equal to 0. Okay. So it has the properties of white noise. The autocorrelation of a white noise sequence would be 1 or some non-zero number for 0 shift and it will be 0 for everything else. In this particular case, it's almost there. So it is 127 and it's minus 1 for everything else. So if I normalize it, it is 1 and minus 1 by 127 for all of it. Of course, if you shift it by 127, then it's basically the same as a shift of 0. The whole thing repeats. I mean, the sequence itself is periodic, so the autocorrelation, if you run it over the entire thing, that will also be periodic. Okay. So that is why it is also quite useful. It has these properties of randomness, or it is like a white sequence. But it's not random, it's fully deterministic, right? Because you know the state machine, so if you know the initial state, you can definitely compute everything that comes out of it. But it has the properties of white noise or a random sequence. So that's what is interesting about it. And that's why it is used to test. It's used in the place of data to test. So it has these random properties which are somewhat like the data. At the same time, it is also fully deterministic. So if you send it, you know what you should get in a communication link that has no errors. So you can do things like you send this, it exercises the system the same way random data does, but you also know what you sent. So you can compare it with what is sent. But you don't need to have access to the sent sequence, right? You can have the transmitter here and the receiver here. As long as you know that the transmitter is sending this pseudo-random sequence with 7 shift registers, I can generate exactly the same thing. Okay? It's not that I need the access to the clean version of this data. Okay? So I want to compare the output of this to what was sent at the transmitter. But what was sent at the transmitter, I can generate using another circuit of this type. No, that is okay. The timing all has to be taken care of. But I know exactly what bit pattern was sent. So one like kind of brute force way to do it is I generate the same thing. So I try to match it. Okay, it doesn't match, then I shift it by 1, I try to match it. And if it's PRB of 7, I know that I have to try it 127 times and something has to match if it is correct. If nothing matches, that means that there are bit errors. Okay. But the important thing is it is some deterministic sequence which has autocorrelation which looks like white noise. Why is it equal to minus 1? No, I have not worked it out and we don't have to do it here. You can refer to some. It's not a like very obvious thing. But it turns out that like you said, the number is odd. So you have 127 products. If you do this in the summation, there are 127 terms. So 63 of them will be plus 1, 63 of them will be minus 1 and there will be one extra minus 1. That's what it cancels to the extent that is possible. Okay. I don't know. This comes from this polynomials and stuff like that, groups and polynomials. No, it signifies exactly that it looks like noise. No, what do you mean? No, because your communication link works with random data, right? So if you put a periodic data, you won't exercise your communication link as severely. Because you will not have cases like you have a certain number of ones followed by a 0, followed by a certain number of ones and so on. There are various combinations. If it's purely random data, every combination is possible. So this approximates that. This is something like the random data that, let's say you are talking on the mobile phone and some bits are, it is digital transmission, so some bits are being sent out. Of course it's random, right? But you can't test it with that because then that becomes too, I mean it's not totally non-standard, right? It's like generating something totally random. And also in a scenario where you don't have access to the clean version of the data, you can't compare it with what was sent. So this gives you some deterministic way of generating a signal which has some properties of random data. That's why it's useful. And in a way you can think of it as an exhaustive test, right? So you have 7 bits, you send all possible 7-bit combinations and you test the circuit. That's one way, that's another way to think about it. Now if you, and this in general, this is normalized so that the value at m equal to 0 is 1, okay. And in general, if I use n shift registers, it becomes minus 1 by 2 to the n minus 1, okay. So the magnitude of these non-zero elements reduces, okay. So if you have a larger n, the period is longer, so it takes long time before it repeats, so it looks more and more like noise, okay. So typically what is used in testing communication links is you use PRBS 7 because it is simple, but there are other standard values. I mean these are kind of arbitrary standards, but they have become standard. So there is PRBS 7, 15, 23 and 31. These are typically what people tend to use. So 2 to the 31 is how many bits? What is the period of that? Huh? How much is 2 to the 31? 10.9, it's 1 billion. Okay. So 2 to the 10 is approximately 10 to the 3. So 2 to the 30 is 10 to the 9. Okay. So that's a very long period. So that is very much noise-like. So this treatment is very superficial. This is not about how it came about, and there are a lot of interesting theoretical aspects of maximal length sequence generators. But I am just giving you an idea of why it is used. Okay. The reason it's used is because its autocorrelation looks like that of noise. And the pseudo-random sequence is unique in that, okay, with some obvious transformations. So firstly, I can switch the 2 logic levels. I can make all 0, I mean I can do this, okay. I can take the output and invert it. If I do that, the autocorrelation will be exactly the same. It will not be any different. Okay. Meaning there will be one dominant one and the rest of it will be very small. So that is a trivial transformation. And also I can take the maximal length sequence and reverse it in time. So I can reverse the order of it, and that will also have the same properties. Okay. So it's a useful block to have when you're testing out communication blocks. And you make the PRBS generator. So let me call it PRBS N generator. That is using a shift register of length N. You take XOR of the last output and many others. So I say others very vaguely because it's not always just one bit. In some cases it is multiple bits. When n itself is of the form of 2 to the some integer, it turns out you have to feed many bits back. XOR is fed to the first. So let's say the feedback taps are n, which will always be there, and then something else like n1, n2, n3. That is, you take the nth output n1, n2, n3, XOR all of them and feed it back to the input. So if this works, it turns out that to take n, n minus n1, n minus n2, n minus n3, that will also work. So for instance, here I take the 7th one and the 6th one, but instead I could also connect it to the first one, that is 7 minus 6. I take the 7th one and the first one, that will also generate the sequence. It will not generate the same sequence, but it will generate the time reverse version of the sequence. So it's a pretty interesting block. I don't think so. No. If you keep an inverter where? So let's say somewhere in the middle. I don't think so. Actually, I don't know. But no, this is something I know as a fact. You can refer to the theory to get that. So, I mean, are you convinced that it will be periodic? Is that okay, or it could be aperiodic? Why? Huh? So what? I mean, with only 3 states, I can make it non-periodic, right? No. It's a state machine, so if you get some state, then the evolution from that state is some fixed one, okay? So if you initialize it all once, then if it later somehow comes back to all once, it will have to restart. So the distance between the two all one states is the period of the sequence. Okay, so there are lots of references. I can just send you some if you want to learn more about the theory and so on. For our purposes, the value is that it is a deterministic sequence which has properties of purely random sequence. Okay. Okay, so the next question was basically about transmission and equalization. The channel that was given was of the form, it's a 8th order filter, not just 8th order filter, it's a filter with 8 coincident real poles, okay, cascade of 8 first order sections. So I just chose this for simplicity. This is not meant to be reflective of any real channel, but the pulse response it gives you is of this sort, which is quite commonly encountered. Almost anything gives you some pulse response of this type. And the peak is treated as a cursor, and you look at 1 nanosecond before and after, and also integer multiples of 1 nanosecond afterwards. And I asked you to consider 2 cases where the eye closure is 50% and where the eye closure is 90%. That is, eye opening is 10%. Okay. It turns out that for 50% eye opening, what is omega p? Huh? 650 megahertz. It's about 1 gigahertz, I think. Omega p is about 2 pi times 1 gigaradians per second, or 1 gigahertz. For 10%, it's about 0.67 gigahertz or something of that sort. Is that correct? Yeah. So if you got that much right, I think the rest of the stuff is quite simple. And I also asked you to ignore all of the impulse response lasts infinitely long, but I asked you to ignore everything beyond, everything below 1%. So 1% I had said that is normalized to this. I don't know, some of you have taken 1.8 volt pulses. Why is that? Many of you have done this simulation with pulse amplitude of 1.8 volts. So that's the supply voltage of the technology, but there is no significance of that here, right? This is a purely linear simulation. It's easiest if you do it with 1. So everything is normalized neatly. I mean, there's nothing wrong with it. The only thing is maybe when you're interpreting the tap weights and so on, you get some mistakes. Okay. Yeah. Yeah. No, that's true. You can do it with anything else. The easiest is 1, right? That has some nice like unit pulse this thing. Of course, you can do it with 2.5 or anything else you want. But also, what I want to point out is just because the supply voltage of the technology is 1.8 volts, it has no significance here for this analysis. Okay. So you can just do it with 1 volt and then scale everything up. So, and this 1% of course should be rare when that is 1% when this related to this one. Okay. It's not 1% of 1.8 volts or some high voltage if you assume that. So it can. What's that? Why? Then it was not 10%, I think. How did you go about finding the eye opening? What's that? Yeah. 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 Nearest what? Yeah, yeah. So what did you do? You should have reduced the bandwidth, increased the bandwidth in that case, right? Okay, firstly, how did you, oh, you got higher value for this. No, if it's higher value, the eye opening should be even higher. Okay. If you have a very large bandwidth, if you had infinite bandwidth, you get 100% eye opening. Omega p equal to 4 gigaradians per second, not gigahertz, right? So this is about this effect corresponds to this, I think, roughly, right? Isn't it? So that is 10%. But you said you got more than 10% for that. Okay. Okay. Maybe, I mean, if it is 11%, I don't care. If it is 20%, then it's a wrong answer. But no, this 4 gigaradians per second is 0.67, something like that, 0.63 gigahertz or something. Yeah, I said if this is 1, this is half, 0.25, the next one is 0.005, you ignore this and everything beyond that. So, no, obviously, I mean, this is an IR response, so the number of taps is infinite, but you don't have to worry about things that are less than some value. And in this case, I chose the value to be 1%. Okay. So everyone got this, these two values? And how many taps did you get? In, let's say, when, for 1 gigahertz, 3 taps. So in addition to the cursor, you get 2 taps in this case. And in this case, you get cursor plus 3. That is, in both cases, you get 1 before the cursor, and in the second case, you get 2 after the cursor. Okay? Then what? Yeah. So, for zero forcing, so now, if you just look at the discrete time response, you can either put the cursor at time equal to 0 or some other time. It doesn't matter. Finally, you can only implement causal stuff. So, this is the case for 0.67 gigahertz bandwidth. And your equalizer will look like something. So, this is again some arbitrary choice. I said you use the number of taps in the equalizer as many as there are in the response. So, you should actually use higher if you want to get better equalization, but just to standardize the problem, I did this. Okay. So, this will be something like this. And the result, if I convolve these two, what I get is I get something starting from 0, perhaps something of this sort, and the main, because each one has a delay of 1 for the cursor, in the equalized response, there is a delay of 2 for the cursor. I don't know if it's positive or negative, I am just plotting it. So, there will be 7 of them. Okay? Yeah. I mean, you have 2 post cursors in the response, right? So, isn't it better to...
No, but in this case, for example, if we assume 0% is going on, the last term would be...
If you assume 0 forcing is?
This fine.
Yeah.
If we have done 0%, the last remaining cursor would be 3 of the order 2.
Would be? Okay.
This, on this side, it will be of the order 4.
So, you are saying it's the product of these two is one of them and the product of these two is the other one, right? You are talking about this term and the relative magnitudes of that. Okay, what about it?
This would be of the order 2, this would be of the order 4.
Order 2, why?
I mean, just
Why? I mean, why will this be of order 4?
in the case of two-tap equalizer when we design,
Yeah.
the order kept on increasing as we increase the length of the equalizer response.
Okay.
As we went to the farther terms,
Okay.
there would be of the order of the form.
No, but if you, so here you can only set, you can set this to 1 and these 3 to 0, right? Is this what you did? Okay. So then I don't think these two, I don't think this will be of order 3 and this will be of order 4. I think both will be of order 3. I don't know. I have to also think about it. But what he is referring to is, he says maybe you get a better response if you choose 2 precursor taps and 1 post cursor tap. Meaning, here we forced some things to 0 and we left the other things as they were. Okay. Whatever is left as they were, whatever is left will be of lesser magnitude if you choose it differently. That is the motivation, right? So, but I am not sure that these two will be of, I don't think this will be of 3rd order and this will be of 4th order. I think they will be of the same order. Order meaning, okay. In case of, we had certain ISI. So, let's say this is 1 and this is alpha. If you do 0 forcing with 1 post cursor tap, you will get 1, 0 and something like alpha square. If you do it with 2 taps, you will get 1, 0, 0 and something like alpha cube. So, his claim is this will be alpha cube and this will be alpha to the 4. Is that right? Something like that. So, what do you want to do? Instead of this, you want to weight the other side.
If I instead have 2 precursors and 1 post cursor,
Okay.
we have 3 on both things. It's 3 elements on the precursor side and 3 elements on the post cursor side and the equalizer.
Okay.
In which case, both will be of order 3.
Yeah.
In this case, one is deteriorating the other. If we look at the sum of the magnitudes,
Yeah.
since
Yeah.
the second order, this might deteriorate the other.
So, you are saying this will be alpha square and this is,
Alpha 1.
yeah. Actually, I am not sure that this will be alpha to the 4, but if it's alpha cube also, it probably deteriorates. Yeah, that's actually a good idea. But somehow, I have to work it out and see. Yeah. So, did you work out the coefficients? Does it work out like that?
So, I did it with 2 precursor and 1, that was better.
That was better.
Slightly better.
Okay. I mean, slightly meaning what, did you report that in the, okay.
I calculated
No, but you can just take, you can just look at the taps weights in the equalized response. See, if it is like this, if this gives you alpha square and that gives you alpha cube, this will be very obvious if you simply look at the discrete time equalized response. So, do you remember the answer? Anyway, I have to work it out also and see. It will be, if you use 2 precursor taps, it will be more symmetric. But, yeah, this one I have to see to be fully convinced. Anyway, the motivation was that you change the, I said use 4 taps, but I also implicitly assume that you will have 1 precursor and 2 post cursor. But the suggestion is to use 2 precursor taps so that the residual ISI is smaller. Okay. No, you use 2 precursors and 1 post cursor. So, you still use you use cursor, here you are using 2 post cursor and 1 precursor, but then you don't have a response like this. You have a response that looks like, for the equalizer, you have a cursor here, 2 precursors and only 1 post cursor. Okay. So, we are not increasing the number of taps. We are just changing the relative weights of the taps, or basically the positioning of the cursor. Yeah, the only thing I am not 100% sure is if it will deteriorate, it looks like the post cursor ISI in the equalized response. But I have to work out the magnitudes and see if it's always, I mean, if it's always obviously better or it could be worse also.
Sometimes we may not be able to
do what?
Choose a different type of equalization response.
Why?
Because the products, if it turns out that the term which we can make 0, and if they are single without sums.
Yeah, that will be only at the end, right? So, always you will have a sum of at least 2. It is a convolution after all. You overlap and sum. So, at the 2 ends, you will have just a product of, so you will get a product of, these 2, that is at one end, and you get the product of these 2, that's at the other end. Those are the only 2 that you get as just, as single product. The rest of it will be some summation of products. Okay. And of course, if you did this bandwidth calculation correctly, if you take the sum of the magnitudes of these, right, you should have got the consistent answer. You should get 50% or 10% as the case may be. Okay. And in fact, for 10% case, you will see that the precursor and postcursor tabs are pretty large. They are almost half of this. Okay. Obviously, not quite half, but somewhere there. So, zero forcing. And what about the other one, LMS? How did you do that? How did you calculate the taps? How many pages did that take you?
No, that's it. I mean, it is symmetric matrix which comes out.
Okay.
And we have to solve it. So once we do it, we can write it down for any number of tabs.
Okay. Okay. What else did you do? How did you guys get the mean square, minimum mean squared error, tabs for minimum mean squared error? Huh? No, worked it out how? You mean you differentiated and set it to 0 and was that easy enough? I don't know. I think I would not attempt this actually, but so you are aware of this LMS fitting and stuff like that? So if I give you like 100 points and I want to pass the best fit straight line through it, how would you do it? If I have 2 points, then clear, there is only one straight line that passes through the 2 and that is the best fit. But if I have 3 points and I want to pass the best fit, in this case best fit meaning the mean square error between the line and the points must be minimum. How do you do that? You must have done this in math long ago. Huh? Yeah, what is that? No, I know, but how do you do that? That is minimum mean square, huh? I mean, you remember some formulae, things like that? Does this ring a bell? No? Oh, you have not seen this? Okay. If you have not seen it, it's fine. But an easy way of doing mean square fitting is this. So let's take the problem that I just described. I have many points, not 2, lot more than 2, and I have to fit a straight line. Or in general, I have m equations and n variables, and in this case, m is much larger than n. Okay, so clearly there may not be an exact solution, but I have to find the variable such that the error between the fit values and the points are minimized. Okay, this is also a pretty common scenario. You make measurements and they are not always exactly in the straight line, right? So let's take you have let's say 10 points given to you, x1, y1, x2, y2, and so on, and x10, y10. Again, I'm going to outline the method. I'm not going to prove how why it is minimum mean squared error, mainly because I don't know why it is minimum mean squared error. I've forgotten how to prove it, but it comes out from this linear. I mean, you must have done it in like math 2 or 3 or something of that sort. So if you forgot it, then you can remember. You can imagine how long ago it was for me. So this has to, and the equation for a straight line is y equals mx plus c. And in this case, I need to determine m and c so that the error between the straight line and these points is minimum. And error is, I am talking about the sum of squared errors. Okay. And this I can rewrite as minus mx plus y. So this equation, if I write it for each of these points, will look like this. So note that here x1, these are the known things and m and c are the unknowns. Okay. M times c equals, this is the set of equations I have. I have 2 variables and 10 equations. Okay. So obviously I can't invert this. If I had only 2 variables and 2 equations, and I could invert it, and that's the exact solution for a linear system. So this, if this matrix is A, and this is some vector y, okay. So I can't invert this, but if I multiply by A transpose on both sides, this becomes a square matrix, okay, which I can invert. So there is some kind of a solution here, meaning this is some kind of a trick I did. I multiplied both sides by A transpose, that is fine. Now I say M and C equals A transpose A inverse, A transpose y hat. Okay. A is basically this matrix which you get from the known points or x's. Okay. So this looks like a kind of closed form solution. Of course, you solve it using the computer when these matrices are large. And it also turns out that the value of m and c you get from this is the best mean squared error, least mean squared error fit for the given points. Okay. You can use something like this for idea. Imagine that you would use something like this, but you have more stamina than I imagined, so you did the differentiation. So the equations that you get from, do you recognize that the equation that you get will be of this type, right? Your coefficients G0, G1, G2 will be here, and these terms will be related to some, the response of the channel. Okay? Huh?
They are equation constants.
Yeah. Yeah. So these will be the response of the channel, and this will be the equalizer taps, and the output will be whatever you want it to fit to. In our case, we want it to fit to. So in the kind of thing I described, if you have one precursor and two postcursor, and also the first response has an index of 0, this is what you want to fit it to. Okay. So you can try this. I think this is easier. Like all this needs is to set up the A matrix in MATLAB. You just group the terms appropriately, and after that you can do this inversion. Okay. So do you recall this now, or even now it is not? I think you have not done it in that case. Okay, and also the coefficients won't turn out to be very different from the other case. Okay, the boost may be a little bit less, but it will be about the same. Then how did you implement the equalizer? So now these are the coefficients based on the discrete time response. Then what did you do after that? So I think if you did Verilog A, okay, those of you who did Verilog A, what did you do? How did you do that? Yeah, so you just use the delay operator or something. So there are various options. If you use Verilog A, you can use delay, or you can use, there is something known as, there is something to implement Z transform filters. Okay. If you specify the sampling rate, I forget the name. For Laplace transforms, it is Laplace underscore ND and so on. What is it for Z? That's right. It's called, it's some non-intuitive name. If you want to implement a Z transform filter by specifying the numerator and denominator, you can use this command. And similarly, if you want to specify the poles and zeros, there is also something like this, a whole bunch of combinations, but they all implemented the same way. So they do this delaying and summing with the coefficients. You have to specify the coefficients. Okay. So if you do it in Verilog A, it's actually things are very simple because everything is taken care of for you. Those of you who did it in MATLAB, what did you do? So you oversample the signal and you delay it and add it, because you want to get the continuous waveform, right? Meaning you want to get many points per cycle. In the discrete time response, you have only 1 point per symbol period. So to plot the waveform, you need a lot more points. So you get the pulse response and the channel response, which is oversampled heavily. So you can use maybe 25 points per period or even more. And then you can delay that and add, and you get the I. Okay. Is that what you did? Did someone do it significantly differently from this? Yeah, that's basically all that's there to it. Once you determine the coefficients, it's a matter of keeping track of terms. So one thing that in MATLAB, so this is also something that you should learn, that MATLAB is very easy to solve, but it does everything in discrete time, right? There is no, the x-axis, or it's just a list of numbers. It doesn't have any significance. So when you do continuous time problems in discrete time, there will be this, so basically this is what you do in continuous time, and a discretized version of this is to take the samples of x and samples of y and do this. And what is missing is this delta t. So you have to multiply this by ts. So if you go between continuous and discrete time, you will always find multiples which are either the sampling period or the sampling frequency occurring frequently. Okay. So sometime when you have time, we can go through that transformation, that the boundary line between continuous time and discrete time. We use discrete times and DFTs to do a lot of computation, but our quantities of interest are usually in the continuous time. But you have to keep the units right. So to do that, you have to get the scaling factors correctly. So sometimes we will discuss that. But that is basically, of course, if you omit this, you will get a hugely different answer, right? Because TS is 10 to the minus 9 in this case. So you will get some weird answers. But weird meaning it will be scaled, that's all. The shape will be the same. Okay. So that's pretty much it that you have to take care in MATLAB. And what happens with PAM4? Does it? Does eye opening improve a lot? How much?
At least 10% channel went from 70 to 1% to 90%.
Yeah, but that is percentage. But what about the voltage? Voltage is less. Okay. Yeah. And what about the horizontal eye opening? So the eye looks something like this. This is the horizontal and this is the vertical. Reduces in PAM. In absolute terms, in absolute number of picoseconds. Okay. It increases. Are you sure? How much is it? Actually, for vertical eye opening, in terms of the number of millivolts, it does reduce simply because you have, even if you have perfect PAM eye, you have only 1/3 the amplitude in case of PAM. So, and your equalized response is, so again, I asked you to compare both the equalized and the unequalized response. The unequalized response for PAM4 is certainly better, right? There is some eye opening for the, for this 4 gigaradians per second case, that is 600 megahertz. In case of binary, it's almost completely closed. In case of PAM4, it is open still. It is visibly open. So it is better. But after you equalize it, you can equalize the binary data to the full amplitude, whereas here, when you do the best equalization, you get 1/3 the amplitude. So that may or may not be, that may not be an advantage at all. Although percentage-wise it is very well open, it may not be an advantage. The other thing to consider is the horizontal eye opening. Now the period is twice as wide, but then because of all these transitions, even the best PAM4 eye has less than 100% eye opening. Okay? So we'll discuss this, take this up later in the next class or something. But think about it. Even the best PAM4 eye, if you don't have zero rise and fall times, it will have non-zero eye closure or less than 100% eye opening. Whereas if you have a perfect binary eye, regardless of rise time, if you don't have any ISI, it will have 100% eye opening. Any questions?